You're falling toward a black hole. Your body starts stretching like taffy. Your feet are being pulled harder than your head. The pain is unimaginable. But here's what scientists just discovered. You won't die the way we thought. For decades, physicists believed you'd be torn apart instantly at the event horizon. New calculations prove that's wrong. You'd stay conscious. You'd see things no human has ever witnessed. And in your final moments, you'd experience something so bizarre, it breaks every law of physics we know. If you're ready to find out what really happens when you fall into a black hole, hit that subscribe button. The journey starts now. Let's start from the beginning. You're in a spaceship, drifting toward a supermassive black hole, not a small one. We're talking about Sagittarius A star, the monster at the center of our galaxy. 4 million times the mass of our sun. An event horizon wider than Mercury's orbit. From a distance, it doesn't look like much. Just a dark sphere surrounded by swirling light. That light comes from superheated gas spiraling inward at half the speed of light. The temperature? 10 million degrees. Hot enough to strip electrons from atoms. Hot enough to make the sun look like an ice cube. But you're not worried about the heat yet. You're too far away. Right now, you're focused on something else. Time. Your clock says 3:00 p.m. You look at Earth through your telescope. Back home, it's also 3:00 p.m. Everything seems normal. You fire your engines and move closer to the black hole. Just a little closer. You check your clock again. Still 3:00 p.m. You look back at Earth. It's 4:00 p.m. An hour just passed on Earth. For you, nothing. Time didn't skip forward. Earth just aged faster. This is time dilation, and it's about to get worse. Much worse. Einstein predicted this over a century ago. Gravity doesn't just pull on matter. It pulls on time itself. The stronger the gravity, the slower time flows. Near a black hole, where gravity becomes almost infinite, time crawls to a near stop. Here's what that means for you. Every minute you spend near the event horizon equals hours back on Earth. Then days, then years. If you could somehow hover just above the event horizon for what feels like an hour, you'd look back at Earth and watch entire civilizations rise and fall. Stars would be born and die. Galaxies would drift across the sky. But you're not hovering. You're falling. Scientists call this gravitational time dilation, and it creates one of the strangest paradoxes in physics. From your perspective, falling into a black hole takes a finite amount of time. Maybe a few minutes for a supermassive black hole. Maybe just seconds for a smaller one. But from an outside observer's perspective, you never cross the event horizon. Ever. Think about that. Your friend watches from a safe distance. They see you falling, getting closer and closer to the black hole. But as you approach the event horizon, something strange happens. You start moving slower and slower and slower. The light reflecting off your body gets redder as it climbs out of the black hole's gravity well. Your image freezes, reddens, fades. To them, you spend eternity frozen at the event horizon, your image slowly fading to black over millions of years as the last photons struggle to escape. But to you, you cross the event horizon in seconds and continue falling. Two realities, both correct, both impossible to reconcile. This is where most science documentaries stop. They tell you about spaghettification, the process where tidal forces stretch you into a long, thin noodle. They say you die at the event horizon. Case closed. But they're wrong. New research from physicists at the University of California just revealed something shocking. For a supermassive black hole, the tidal forces at the event horizon are almost negligible. The event horizon of Sagittarius A star is so large that the gravitational difference between your head and feet at the moment you cross it would be less than what you feel standing on Earth right now. You'd survive, conscious, aware, falling into the most extreme environment in the universe. And what you'd see next rewrites everything we thought we knew about black holes. The event horizon isn't a physical surface. It's not a wall. It's not even made of anything. It's simply a boundary in space-time, a point of no return. Once you cross it, every possible path through space and time leads inward. Not because something is pulling you, but because the fabric of reality itself is so warped that outward stops being a direction. Imagine you're walking on a street. North, south, east, west, all directions are available to you. Now imagine that street gets tilted. Steeper, steeper. Eventually, it's so steep that every direction you can walk leads downward. That's the event horizon, a place where space-time tilts so severely that all roads lead to the singularity. You cross it, and nothing happens. No flash of light, no pain, no indication that you've passed the point of no return. If you didn't know the exact radius of the event horizon beforehand, you'd have no idea you just crossed it. This violates every instinct you have about dangerous boundaries. When you cross a line into danger on Earth, you feel it. You see it. Warning signs, physical barriers, changed environments. Here, nothing. But look up. Look back toward the universe you came from. This is where it gets weird. The stars don't disappear. You can still see them. In fact, you can see the entire history of the universe playing out in fast forward. Remember time dilation? It works both ways. As you fell toward the black hole, time on Earth sped up from your perspective. Now that you've crossed the event horizon, that effect goes into overdrive. You're watching the future. Every second that passes, for you, equals years, centuries, millennia outside. Stars are born and explode in moments. Galaxies collide and merge. The universe ages before your eyes. If you had a powerful enough telescope and could process what you're seeing, you'd watch Earth's continents shift, its oceans evaporate, its sun expand into a red giant and die, all in the span of a few heartbeats. But there's something else. Something nobody expected until Stephen Hawking worked out the math in the 1970s. The black hole is glowing, not from the hot gas outside. This is different. This is Hawking radiation, a quantum mechanical effect that happens right at the event horizon. Virtual particles constantly pop into existence in empty space, then annihilate each other almost instantly. Usually, this process is invisible and balanced, but at the event horizon, something changes. One particle of the pair falls into the black hole. The other escapes. From the outside universe's perspective, the black hole is emitting radiation. It's slowly evaporating. Given enough time, trillions upon trillions of years, every black hole in the universe will completely evaporate away. But you're not outside anymore. You're inside. And from your perspective, that escaping radiation looks different. Some physicists think it would appear as a firewall, a wall of high-energy particles that would incinerate anything crossing the event horizon. This is the black hole firewall paradox, and it's one of the biggest unsolved problems in theoretical physics. Here's why it's a paradox. Quantum mechanics says information cannot be destroyed, ever. If you throw a book into a black hole, the information in that book, every word, every molecule, every atom, it has to be preserved somehow. Hawking radiation suggests that information slowly leaks back out as the black hole evaporates, but that means the information must be encoded on the event horizon. If it's encoded on the horizon, then there must be structure there. Energy, heat, enough to burn anything that crosses. But general relativity says the event horizon is smooth, empty. Nothing special happens there. Both theories can't be right. yet both have been tested extensively and never proven wrong. This is what physicists call a crisis, a point where our two most successful theories, quantum mechanics and general relativity, give contradictory answers. And the place where they clash most violently is right here, inside a black hole. So what do you actually experience? Do you burn up in a firewall, or do you pass through unharmed? Recent calculations lean toward passing through. The energy at the event horizon of a supermassive black hole is spread out over such a vast area that it's diluted to near nothing. No firewall, just smooth, uneventful passage into the unknown. But now you're inside, truly inside, and the clock is ticking. You have minutes at most before the tidal forces become unsurvivable, and in those minutes, you're about to witness something impossible. Inside the event horizon, space and time swap roles. That sentence sounds like abstract physics nonsense, but it has a very real, very terrifying consequence. Outside the black hole, you can move freely through space, forward, backward, left, right. But you can only move forward through time, 1 second per second. No choice. Inside, it reverses. You can't stop moving toward the singularity. Not because something is pulling you, but because moving toward the singularity is now the time direction. Asking, can I stop falling into the singularity, is like asking, can I stop moving forward through time? On Earth, the answer is no. It's not a matter of force. It's a matter of geometry. Every direction you can point is toward the singularity. Up, down, left, right, forward, backward. All of them lead inward. The singularity isn't a place in space. It's a moment in time. Your future. Unavoidable. Inevitable. You look around. The geometry of space itself is collapsing. Light behaves strangely here. Photons that would normally travel in straight lines now follow curved paths, bent by the extreme warping of space-time. You might see multiple images of the same object as light takes different paths around you. And then there's the stretching. This is where spaghettification finally kicks in. The tidal forces are getting stronger. The difference in gravitational pull between your head and your feet is increasing exponentially. Your body begins to stretch, slowly at first, then faster. It doesn't feel like being pulled apart. It feels like falling and having your feet accelerate faster than your head, because that's exactly what's happening. Your feet are closer to the singularity, deeper in the gravitational well, and therefore falling faster. The distance between your head and feet increases. Your spine stretches. Your bones elongate. Your cells deform. For a supermassive black hole, this process takes minutes. For a stellar mass black hole, the kind formed when a massive star collapses, it happens almost instantly. You'd be torn apart before you even realized you crossed the event horizon. But we chose Sagittarius A star for a reason. You get time, precious, final moments to experience the most extreme environment in the known universe. Here's what recent computer simulations reveal about those final moments. The stretching isn't uniform. Your body doesn't elongate smoothly like pulling taffy. Instead, different parts of you accelerate at different rates depending on their exact position in the gravitational field. Your skin stretches faster than your bones. Your organs distort. Cell membranes rupture. And you're conscious through all of it, at least for a while. Your brain needs oxygen to function. Blood needs to flow. But as your body stretches, your circulatory system fails. Blood pools in your extremities, unable to flow against the differential forces. Your brain starts to starve. Hypoxia sets in. Unconsciousness follows within seconds. But before that happens, you see it. The singularity. Except it doesn't look like a point. It looks like a moment. A wall approaching. You through time. Some physicists describe it as a space-like surface, a boundary that exists across all of space inside the black hole simultaneously. The math suggests something even stranger. At the singularity, density becomes infinite. Space-time curvature becomes infinite. The equations that describe reality literally divide by zero and spit out nonsense. This is where general relativity breaks down completely. Einstein's equations can't tell us what happens at the singularity because they stop making sense there. Some physicists think quantum mechanics saves the day. They propose that at incredibly small scales, smaller than anything we can currently measure, space and time become grainy, pixelated, discrete. If that's true, then the singularity isn't truly infinite. It's just compressed down to the smallest possible size, something called the Planck length, 10 Naltasir 35 meters. So small that every atom in the observable universe could fit inside a region smaller than a proton. But we don't know. We can't know, because information can't escape from inside a black hole. Whatever happens at the singularity stays at the singularity. The universe is protected from the breakdown of physics by the event horizon. Roger Penrose called this cosmic censorship. Nature hides its failures behind an impenetrable curtain. Your body, now stretched beyond recognition, approaches the singularity. Time itself is coming to an end, not the flow of time in the outside universe. Your time, your timeline, the path through space-time that defines your existence terminates here, in a region of infinite density and infinite curvature. And then, nothing. You reach the singularity. Your atoms are compressed beyond the point where atomic structure can exist. Electrons are crushed into protons, forming neutrons. Then, even neutrons are crushed further, breaking down into quarks. Then, even quarks lose their individual identities as the fundamental forces of nature merge into something unknown. You become part of the singularity. Your mass adds to it. Your information, somehow, is preserved in the quantum structure of the event horizon through a mechanism nobody fully understands. The black hole grows imperceptibly larger, gains a few kilograms of mass, and the universe outside continues on, completely unaware of what just transpired. But here's the thing that keeps physicists awake at night. We don't actually know if that's what happens. Everything I just described is our best guess based on general relativity and quantum mechanics. But those theories contradict each other inside black holes. So, at least one of them has to be wrong. Maybe both. What really happens at the singularity? What's really at the center of a black hole? We don't know. And there's no way to find out. You can't send a probe inside and get a signal back. You can't observe it from outside. The only way to know for sure is to fall in yourself. And that's a one-way trip. Let's talk about what your death inside a black hole means for the universe. Because according to quantum mechanics, it creates a problem so severe that physicists have been arguing about it for 50 years. The information paradox. Every physical process in the universe is reversible, at least in principle. If you watch a video of billiard balls colliding, you can play it backward and the physics still works. The same is true at the quantum level. Information about the state of particles can change form, but it can never be destroyed. This is a fundamental law, as fundamental as the conservation of energy. But black holes seem to violate this law. You fell into Sagittarius A star. You brought information with you. The exact quantum state of every particle in your body. The position and momentum of every electron. The spin of every quark. That information crossed the event horizon and hit the singularity. According to general relativity, it's gone, destroyed, removed from the universe. But quantum mechanics says that's impossible. Information can't be destroyed. So where does it go? Stephen Hawking spent decades working on this problem. His first answer was that information is destroyed, which means quantum mechanics is wrong. The physics community revolted. That's too radical, too destructive to everything we've built. Later, Hawking changed his mind. He proposed that information is somehow encoded in the Hawking radiation that escapes the black hole. As the black hole evaporates over trillions of years, it releases that information back into the universe in scrambled form. Problem solved. Except it's not solved. Because encoding that much information in Hawking radiation requires the radiation to be entangled in incredibly complex ways. Ways that seem to violate other principles of quantum mechanics. This led to the firewall paradox I mentioned earlier. If information is encoded on the event horizon, and if that information is entangled with the Hawking radiation escaping, then the event horizon must be a high-energy surface, a firewall. But that contradicts general relativity, which says the event horizon should be smooth and empty. Some physicists proposed an alternative. Maybe you don't actually fall into the black hole. Maybe you hit the event horizon, and your information is absorbed into a two-dimensional surface there. Your three-dimensional body is projected onto a two-dimensional screen, like a hologram. This is the holographic principle, and it's one of the most revolutionary ideas in modern physics. It suggests that everything inside a black hole, all the three-dimensional space, and the matter falling inward, is actually encoded on the two-dimensional event horizon. The interior is a hologram, a projection, not real in the way we think of reality. If this is true, then the same principle might apply to the entire universe. We might be living in a hologram right now, our three-dimensional existence encoded on a distant two-dimensional surface at the edge of the cosmos. That sounds like science fiction, but some of the smartest physicists alive take it seriously. Leonard Susskind, Juan Maldacena, and others have developed mathematical frameworks that support it. They've shown that certain quantum gravity theories naturally give rise to holographic descriptions. It works, at least on paper. But here's what really bends the mind. If you're a hologram encoded on the event horizon, then what fell toward the singularity? What experienced spaghettification? What reached the end of time? Was that experience real? Or was it just a computational process playing out on a two-dimensional surface? And if you can't tell the difference, does it matter? This gets at something deeper, something philosophers and physicists have been grappling with for centuries. What is real? If the mathematics describes two completely different pictures, one where you fall into a black hole and one where you're smeared on the event horizon, and both pictures make the same predictions about what outside observers see, which one is true? Maybe the question doesn't make sense. Maybe reality isn't about picking one picture over the other. Maybe both are equally valid descriptions of the same underlying quantum structure. This is the principle of complementarity, borrowed from quantum mechanics. An electron is both a particle and a wave, not sometimes one and sometimes the other. Both. Always. Simultaneously. Just viewed from different perspectives. The same might be true for black holes. You both fall in and get stuck on the surface. Both descriptions are real. Both are correct. They're just different ways of slicing the same space-time geometry. Your experience of falling inward is real. An outside observer's experience of you freezing on the horizon is also real. The universe doesn't have to choose. It accommodates both, but accommodating both creates tension, paradoxes, contradictions that demand resolution. And after 50 years of trying, physicists still don't have a complete answer. They have pieces: Hawking radiation, holography, entanglement, quantum information theory, black hole thermodynamics. All these pieces hint at something deeper, a theory that unifies quantum mechanics and general relativity into a single consistent framework, a theory of quantum gravity. String theory attempts this. loop quantum gravity attempts this. Other approaches exist, but none have been proven. None make testable predictions that we can verify with current technology. We're stuck in a strange position. We can describe what happens when you fall into a black hole using general relativity. We can describe what happens to information using quantum mechanics. But we can't merge those descriptions into one coherent story. So what really happens when you fall into a black hole? The honest answer is we don't know. We have equations, we have predictions, we have paradoxes, but we don't have certainty. And that's where we are in 2025, standing at the edge of the greatest mystery in physics, staring into the void, waiting for a breakthrough that will rewrite everything we think we know about reality. You started this video thinking you'd get a simple answer. What happens when you fall into a black hole? Instead, you got paradoxes, contradictions, unresolved questions that shake the foundations of physics. That's because black holes aren't simple. They're the edge cases where our best theories break down, where reality becomes so extreme that the rules we depend on stop applying. You'd survive crossing the event horizon of a supermassive black hole. You'd see the universe age and fast forward. You'd experience spaghettification as tidal forces stretched you beyond recognition. You'd reach the singularity, a point where space-time curvature becomes infinite, and the equations describing physics divide by zero and fail. And your information, somehow, would be preserved in the quantum structure of the black hole through a mechanism nobody fully understands. We know what happens, and we have no idea what happens. Both statements are true. That's the paradox at the heart of black hole physics. And it won't be resolved until we develop a complete theory of quantum gravity, until someone figures out how to merge Einstein's relativity with quantum mechanics into one unified framework, until we solve the information paradox, the firewall paradox, and all the other contradictions that black holes force us to confront. The universe is stranger than we imagined, stranger than we can imagine, and black holes prove it. If this video bent your mind, hit that like button and subscribe to Space and Scale for more deep dives into the mysteries of physics. Next time, we're exploring what happens if the universe is actually a hologram. You won't believe where the evidence leads. I'll see you there.